Hello, everyone, and welcome back. We are going to talk about molecular geometry now. And I know that you thought that you left geometry all the way back up on the third floor, but actually, the shape of molecules is going to play a huge part in the polarity of a molecule and how it behaves in various situations. So let's get started. Right before we do, though, you should put this on pause and go and get a whiteboard, a marker, and an eraser. And what I want you to do is come back and draw the electron dot structure for water, H2O. So put this on pause. Okay, so you guys should have done that electron dot structure for water, and this is what it looks like. Now look it, I'm sure that most of you probably drew water in a straight line, like where you have hydrogen and then oxygen in the middle and then the other hydrogen on the other side, like all in a line. And based on what you guys know now, yeah, sure, that would be correct. However, this is the correct electron dot structure, or EDD, that stands for electron dot diagram for water. And the reason why is because of these lone pairs of electrons. So lone pairs of electrons are the electrons that don't participate in covalent bonding. Instead, what they do is they repel each other because electrons all have a negative charge, and so they repel. And as they repel each other, they bend the bonds of the between the oxygen and the hydrogen down, causing it to bend. So from now on, this is the way that you need to draw the electron dot structure for water. All right, so this theory on how the lone pairs of electrons behave is called the VSEPR theory. This stands for valence shell electron pair repulsion theory. And this is a theory that says that unshared electron pairs, also known as lone pairs, repel, and they bend the molecule into shapes. Another example of this can be seen here in our NH3, in our ammonia molecule. And you can see that based on what you know now, this would probably be how you would draw NH3. However, the lone pairs of electrons right up here are going to push these bonds downward so that they're all kind of sprouting off the bottom of the nitrogen molecule, giving it a three-dimensional shape. Okay, so what I want you guys to do now is grab your packets, grab a pen or a pencil, and you need to open up to page 24. Go ahead and put this on pause so that you can do that. All right, hi there. We should be on packet page 24. Sorry, it doesn't look like that. It actually looks like this. So we're looking at how VSEPR shapes molecules. And so back yesterday, you guys learned that intramolecular bonds contribute to the polarity of molecules, but so do their shapes. And so we're going to explore a little bit how their shapes affect a molecule's polarity, whether one side of the molecule is positive and the other is negative, meaning that it's a polar molecule, or whether the shape allows for the equal sharing of electrons among all of the atoms in the molecule, making that molecule non-polar. Okay, so on the next page, page 25 in your packet, what I write, you write. Easy peasy, right? Okay, so my first example here is nitrogen, elemental nitrogen, which is N2. The number of atoms that I have here is 2. I simply have 2 nitrogen atoms. And my electron dot structure for nitrogen is going to look like this. It's got a triple bond in between my 2 nitrogen atoms. In the next column, are there unshared pairs around the central atom? Well, the thing is that we don't have a central atom. If you have only 2 atoms, neither of them are in the center. So this is just kind of like not applicable, or NA. The bond angle here is 180 degrees. Think about the atoms as being 2 points in a line, and a line always has an angle of 180 degrees. And we are going to call this shape linear because it's in a line. Bingo, stop it. Linear diatomic. Di means two, and then atomic refers to atoms. Okay. For our next one, we have CO2, which is carbon dioxide. We have one carbon and two oxygen atoms. That means we have 3 atoms total. And my electron dot structure is going to look like this. Are there any unshared pairs around the central atom? Well, now that I have 3 atoms, my central atom is carbon. That's in the middle. Now, how did I know to draw carbon in the middle? Because carbon is the least abundant of the different species of elements that we have in this compound. So we have only one carbon, so that must go in the middle, and then all of the oxygen atoms have to go around it. So my middle atom here is carbon. I do not have any unshared pairs. I have no dots around the carbon. All of carbon's valence electrons are tied up here in the bonds. So, how many unshared pairs of electrons do I have? I have 0. My bond angle, once again, is 180 degrees. So my name for this is linear because it's in a line. But then I have 3 atoms now. So the prefix here would be triatomic. So I put my 2 linear molecules, I drew them in purple. And now I'm going to take a look at my water molecule here, H2O. Once again, I have 3 atoms here. And my water is going to look like this. Now this time I have oxygen that is going to be in the middle because that is the least abundant species of element that I have because I've got 2 hydrogen and I have only 1 oxygen. So the oxygen has to go in the middle. Do I have any unshared electron pairs? Yes, I do. I have 2 of them. Here's 1 and here's 2. So my answer here is going to be 2. My bond angle, bingo, leave it. My bond angle is 105 degrees. I'm never going to ask you about like the bond angle for water or for any of these bond angles at all. So these are more of like nice to know pieces of information. But this one here, this is bent triatomic because we've got 3 atoms in a bent shape. And again, this one is bent because I have unshared electron pairs around the central atom that push the bonds down. Up here in CO2, even though I still have 3 atoms, there's nothing here to bend the molecule. That's why it's linear. That's why it's straight. So this is where Vesper is coming into play. So if you've got unshared pairs of electrons around that central atom, well, now you're going to have a molecule that's not linear. You're not going to have the atoms distributed like equally. All right, let's take a look at our next one. This is BF3, and this one has 1 boron and 3 fluorine. Excuse me for a minute. Bingo, leave it. And I have 3 fluorine atoms. So here I've got 4 atoms. My least abundant atom is boron, so that's going to go in the middle. And then all around, I have my fluorine atoms. All right, so here is my electron dot structure for boron trifluoride. And do I have any unshared electron pairs around my boron? Do I have any dots around that central atom? No, I don't. So I'm going to put a 0 here. And so what this does is it allows the fluorines to spread out evenly around my boron. So if you think of this as like a circle, it's going to kind of look like a Mercedes-Benz symbol, where boron is here in the middle, and then the fluorines are equidistant from each other all around the circumference of that circle. So the name of this is a flat molecule. So this is called trigonal because we have three angles, and it's flat, so it's trigonal planar. Our next molecule is NH3, and NH3 again has four atoms that are in there. So our electron dot structure for NH3 looks like this. And this one has one lone pair of electrons around the central atom, and these are going to spread out and push the bonds down. And so the name of this shape molecule is called the shape of this one is called pyramidal or trigonal pyramidal. My last one is CH4, and CH4 is our only molecule, or like the only example that we're looking at on this document that has five five atoms in it. Here's the electron dot structure. So you have your carbon in the middle, and the four hydrogens are all around the outside. And I just want you to see that like two of them are in the same plane. You've got this H here that's kind of sticking out at you, and then this hydrogen is kind of sticking out behind the carbon. So that's why I drew it that way. I have no unshared electron pairs around the central atom. This is called tetrahedral. All right, back to keep this page out, and now we're going to go back to our slides. All right, we are back. Let's draw the electron dot diagram, also known as the EDS, or the electron dot structure, for silicon dioxide. So let me get my pen going here. We have silicon in the middle, and we're going to have our oxygens over here at the end. The total number of atoms that I have here, and again, you're going to use your Vesper sheet that we just finished. We have 3 atoms total. We do not have any unshared electron pairs around the central atom, which means that that it's not going to bend. And so this is just like carbon dioxide. We have 3 atoms, no dots around the middle. So this is linear triatomic. All right, let's try one more here. Draw the electron dot diagram for phosphorus trichloride and use your Vesper sheet to fill out the table below. So for phosphorus trichloride, we have, whoops, sorry, there was the answer. So this might be how you drew phosphorus trichloride, and that's a very nice start. However, now we know the Vesper theory. So these unshared electrons are going to push these bonds down, and so here's how you should draw this electron dot structure. All right, so the way that I wanted to do this isn't really working, so I'm just going to show you the next slide here. So you may have drawn your PCl3 like this at first, and that's lovely, except now knowing Vesper theory, you should know that this is how it should look, because these unshared electron pairs are going to bend all of these bonds. And then to fill out the table below, the total number of atoms is 4. And yes, we have unshared pairs of electron around the central atom.